Okay, so we start now the third course this afternoon. So I present here Gonzalo Manzano, who is going to give a course on quantum thermodynamics and thermal machines. So thank you very much, Gonzalo.
So thank you very much, Gabriela and Jose Daniel, for the invitation. It's really a pleasure to be here. It's my first time here in Colombia. So I'm going to talk about quantum thermodynamics. In this mini course, I will touch mostly on two topics inside quantum thermodynamics. First one is fluctuation theorems, and second one is quantum heat engines. So let me just start by saying what is more or less quantum thermodynamics. So quantum thermodynamics is like an emergent area of research, which places at the intersection of non-equilibrium statistical physics and quantum information. So it attracted a lot of attention in the last like 10 or 15 years, more or less. And in a sense, it tries to understand and describe the thermodynamics of quantum processes. So in some sense, it can be seen like an extension of stochastic thermodynamics to systems in which quantum effects cannot be neglected anymore. But it also brings a lot of new questions. So for example, what are the thermodynamic role of quantum effects like entanglement or quantum coherence? Or what about the miniaturization of heat engines? Is there any limit in the miniaturization of heat engines or not? Or also if it is possible to use these quantum effects to enhance some thermodynamic task beyond classical limits. So there are a lot of people that came to this field in the last years, people working like in quantum optics, in many-body physics, in nanophysics, in quantum information, in stochastic thermodynamics, etc. And so this is like an interdisciplinary field, and it's quite open. So there is a lot of research being done right now. So it's rapidly evolving. And the purpose of this course is just to give some introduction, okay, to some of the topics. So, so in this first session, I will talk about some background, which is going to be quantum measurements. And open quantum systems. And in the second session, I will focus on fluctuation theorems. On quantum processes. And in the third one, I'm going to talk about quantum thermal machines. Like heat engines, refrigerators, etc. So let's start from with the background about quantum measurements and open quantum systems. So I would like to start this just by saying that quantum mechanics postulates two types of evolution in his principles. First one is unitary evolution. right? And it just transforms wave functions using unitary operators U, which is equivalent to the Schrodinger equation, right? So you may have some time-dependent Hamiltonian, and your wave function will evolve smoothly and in a deterministic way, right? If I know with certainty the initial state, I will know the final state after some time. This U is this operator, in which you integrate the Hamiltonian over time. So U is unitary, so it verifies this property. On the other hand, quantum mechanics postulates also a very different type of evolution, which is called measurement. Or collapse of the wave function, according to the Copenhagen interpretation. So this is absolutely different from the first one. This is so the first one was deterministic. This is not deterministic. This has an intrinsic probabilistic nature, which means that even if I know with certainty what is the initial state, I don't know what is going to be the state with certainty after the measurement. So we have an intrinsic probabilistic thing. And also, importantly, while the unitary evolution is completely reversible, measurement is irreversible. So with unitary evolution, you cannot change the entropy of a system, the von Neumann entropy. But with a measurement, you change the von Neumann entropy. That means that with measurement, there is some exchange of information with the outside, while in the unitary evolution, there is not. So quantum mechanics doesn't tell us when we have to apply unitary evolution or measurement. So both of them are in the principles of quantum mechanics. But the principle just say when there is a measurement, you apply this. But of course, what qualifies a process as a measurement? This is something which is still under investigation today. So, and leads to many paradoxes that people, for example, in quantum foundations study. For example, Wigner paradox and so on. I will not go into enter in those kind of paradox, but just describe how we can describe measurements in a mathematical way. So the simplest case is what is called the ideal measurements. Which were developed in the 50s by von Neumann and Luders. So essentially, what we do is to write observables, genetic observables, O, which are Hermitian operators, and we can write them as a sum of eigenvalues and projectors. Okay, so those are eigenvalues, and those are the projectors. And this is called the spectral decomposition of this operator. Okay. Any observable verifies this property. It's an Hermitian operator. So the operator, the projectors verify two important properties. First one is that they are orthonormal. If I have some projector pk and multiply by pj, I just get Kronecker delta of kj pj. And the second one is that they provide a resolution of the identity, meaning that the sum over all the Hilbert space of the projectors give us the identity operator. So One example of this is just a spin 1/2 particle. So we can define, for example, one of the observables, one of the possible observables will be the spin in the z direction, which we can write in this form as h bar over 2 spin up minus h bar over 2 spin down, so that we have two eigenvalues, h bar over 2 and minus h bar over 2, and we have two projectors, which will be just get bra of the state up and get bra of the state down. So in many cases, we will have projectors that are observables that have non-degenerate eigenvalues. In that case, the projectors can always be written in this way. So those are rank 1 operators. Otherwise, if they are degenerate, we need to employ a more general way. So we need to sum over another quantum number up to the degeneracy of that eigenvalue, and we will have to introduce this new quantum number inside the kit. Okay, so this will be an extra. However, in most of the cases of this course, I will use rank 1 operators. That simplifies a little bit all the stuff without changing, without changing essentially the thing. Okay, so let's see what is the projection postulates. No, this is the fundamental thing. So the projection postulate says that if I want to measure an observable, then, so if I start in some state psi, and I perform a measurement of the observable O, I will get some outcome, some eigenvalue, okay. And then my state will change to this new state. Which is just the result of apply the projector over my initial state and renormalize. This pk is just the probability that I obtain that outcome, and it can be calculated by the Born rule, which will be just this thing here. This applies as well if my initial state is not pure. If it is a classical mixture, it will be very similar. I will start with some density matrix rho. I will again obtain some outcome OK, and my new state after the measurement condition on the outcome I got will be just this guy. I just need to apply the projectors in both sides and divide by the probability, pk. Here, pk can be written as the trace over the projector times the initial state. So this means that essentially, when I perform a measurement, I project my initial state onto an eigenspace of the operator I am measuring. Okay. And of course, if I perform a measurement and then I measure again, I will get the same outcome, right? Indeed. So this is essentially, well, let's talk about this later. So as a consequence of this property here, we have that the probability is conserved. that is, if I sum over all possible outcomes, the probabilities pk, I will get just one, okay? Because any density matrix has trace one. Okay, so these states, I call them conditional states. And when the projectors are rank one, we have the following. We have that the state after measurement, this one, will be just the projector corresponding to that outcome. So that means that we just collapse the initial state to just that particular outcome. But on the other hand, imagine that I perform a measurement and then I forget about what the outcome was. Okay? In that case, so this is called like conditional state after measurement. But if I forget the outcome, I have to average over the different possible outcomes. So, and this is called the unconditional state, will be just the sum of the probabilities of obtaining each of the outcomes multiplied by the states that I will get for that particular outcomes. So this just gives me this expression here. And this is called the unconditional state. Okay, so any question here? Yes? Sorry?
Que si puedes escribir un poquito más grande.
Yeah, sorry. Yeah. So you cannot see anything of here? More or less. Okay. Okay, I will write bigger. So any question about the content of the... So everyone knows these things? More or less. Okay. Okay, so talking about entropy. So if the result of the measurement is known, so of course this tends to reduce the entropy of a system, right? Because so before I don't know exactly what the outcomes of my system are, and afterwards I will know. So we have that the entropy of the initial state rho is always greater or equal than the conditional state. And if I have rank one projectors, indeed this will be zero. So here's something perhaps important to say is that when I use a pure state, so I have perfect knowledge of my system at the beginning. So in that case, of course, I will not reduce the entropy. It will be zero from the beginning. However, if I use a density matrix, I can also incorporate a classical uncertainty. Okay, my initial state may be a classical mixture of different pure states, right? So and it is in that sense that I can reduce the entropy of my system by measuring. Okay. However, if I consider the unconditional state, I have exactly the opposite. So if I ignore the result, but something has been done in the system, then the entropy of my system will increase. Okay, because there is always the possibility that my system has been disturbed in a way that I don't know. So my uncertainty about the state of my system will increase in general. And of course, the equality here is attained only when, so the quality is when the observable commutes with the initial state that I am measuring. Because in that case, I will not disturb my state. Okay. Okay. So we can put also continue with the example of the spin 1/2 particle. So imagine that I start in a state which is a superposition of the spin up plus spin down. This side is okay for the people in there. So can you see this? Okay. So here we have these two amplitudes that will sum up to 1. And still don't know what is. So I can write this state as a density matrix as well. So I will have some probability to be in state up, and then some cross terms or coherences due to the superposition. Where, of course, these P's up or down are just these amplitude squares, and the C's will be just this A, these things. So for any state, of course, so this means that the two probabilities will have to sum up 1, which is the same as saying that the trace of this state is 1. And also, in order to have a legal state in the sense that it's positive, semi-positive definite, we also need that these coherences are fulfill this property here. So this is the standard. So imagine that we measure, as I said before, the spin in the z direction, so that if I apply the projector so I will have two projectors, right? This one, this one. And if I apply this projector, so what will be my new state? It will be just, so I will apply. So imagine that I get outcome up. Then, so I just apply this to psi, and I divide by the probability, square root of the probability. So I will get just this thing here. The probability will be, of course, as we said before, no? Will be just the trace of P up over rho, which will be just this small P up, right? The probability of down will be just this one here, right? Okay, so my two possible states after measurement will be either this up or down, and what will be the unconditional state? So will be the mixture of these two multiplied by their probability. So P up for the projector up plus P down for the projector down, right? So if we just compare this state to the original state, what we see is that we have lost essentially these terms here, right? Which are called the coherences. So in this sense, so we have modified the state from here to here, and we have increased the entropy of the state, right? Here the entropy was 0 because this is a pure state, but here is not non-zero. Okay. Yes.
I think the post-measurement state should be just the state up and not the projector, right?
Ah, yes, sorry. Yeah. Sorry. Okay, so of course, nothing. So of course, if I would start directly in the state without these two guys, nothing will happen, no? So if I don't have this, imagine I don't start with that. So I already start with a mixture, and I apply the projectors, and I will get the same state at the end. So in that case, I will not change my state, right? And this is, of course, because this state commutes with the set. No? They are diagonal in the same basis. In this case, in the case in which we don't have this, not in the other case. Okay, so this is the ideal measurements, but of course, in any real experiment, we will have situations that cannot be described by ideal measurements. So for example, you may think in photodetection. In photodetection, so you have a photon, the photon clicks on the screen, there is some click in some detector, but the result of the measurement is not having the photon. So the photon indeed gets destroyed. And like this, there are many situations in which these ideal measurements cannot be applied. So in order to go beyond this, what we can do is to go to generalized measurements. And in generalized measurements, what we do is to describe some way of indirect measurement on a system, right? What we have is like, so this is, so the idea is essentially that we have a system, we make the system interact with an apparatus, which is perhaps another system, and then we observe this apparatus after interaction with the system. So in this case, we can apply like unitary evolution to these two guys together. And then we apply some projectors over the apparatus. Of course, one may think, okay, but why you have one apparatus, or why not consider that this interacts with this system, and this with another system, and this with another system, and so on and so forth, and then you just observe the last one. So you could say that, but of course, at some point you need to introduce a cut, no? Which is usually called the Heisenberg cut. So we are going to just consider one step, and of course, what matters is that if you add a new step, nothing changes. No, if this system is sufficiently big so that it gets like classical rapidly, or it has like a quick decoherence, then just one step is okay. So in that case, it's a good approximation. And so that in this case, so let's consider just at a time equal to 0, some composed state of system plus apparatus, which will be a product state, right? That means that these two guys are not correlated at the beginning. Then I will let them evolve. So let them interact so that the apparatus can get some information about the system. So how we describe this? So we can postulate an interaction, so Hamiltonian, which has a system part, an apparatus part, plus some interaction. The interaction may depend on time, so that at the beginning the interaction is 0, then the interaction is switched on, and at some point it's switched off again, so that we can read out the apparatus. So the state of the system at some later time tau will be just this thing here. It's just the result of applying this unitary evolution given by this Hamiltonian over the initial state. Right? With this u equal to this operator here. So in this interaction, what happens is that, so let's make a small picture here. So we have the system, we have the apparatus, they interact through this unitary evolution, so that at the end, so we have this state, rho SA time tau, we will be in general correlated. So these two guys will be in general entangled. They will share both classical and quantum correlations between them. And then what we will do is to just apply some projectors as before, just on the apparatus. So we will measure some properties, some observable of the apparatus, which I call R. So I will get some results, some outcome, RK, so that my apparatus will collapse in some final state pKa, so in some projector of the apparatus only. But of course, this will make, if I read out this outcome, I will learn something about my system. So my system will change because of this readout to some final state, rho S prime, that will depend on the outcome I got on the apparatus. So in this situation, what is the probability of have some outcome? So we can calculate it like using the rules before, just apply to the global system, right? System plus apparatus. So this will be the trace of, let's say, the identity over the system times the projectors over the apparatus of this state, right? Rho SA at time tau. Of course, I can develop this more. So I can then introduce the U, and so the form of this guy, no? Rho S, sigma A, U dagger, etc. Okay, so following this, I can calculate what will be the global state of system plus apparatus when I get some outcome RK. And this just following the rules before. Let me just. Following the rules before, what I get is just something like this, rho SA prime K. It will be identity. It will be the result of applying these projectors on the left and on the right of the state, right? just as before. The only thing is that now we have composite system. Okay, but we are going to be interested not just in the global state after the measurement, but on the state of the system, only the system part. So in order to obtain this, we need to trace out the apparatus degrees of freedom. So, and this is done by, so those are called the marginal states. Marginal state of the system. So this will be this guy here. Is the trace over the partial trace over the apparatus degrees of freedom of this guy here. Right? And of course, as before, we can also calculate this. That will be the conditional again. Conditional state for outcome K. And again, I can calculate what will be the unconditional one if I forget about the measurement outcome. In that case, I will get just this expression. Okay, just I take these guys and then I multiply by the probabilities to get that outcome. Okay, so seems like very big expressions and so on that are not practical, but of course, if we do some small assumptions and specify a little bit more, we can get like more compact expressions for this kind of formalism. So this is what is called the measurement operators and POVMs, which is called positive operator valued measure. It's like the most general form of quantum measurements. So the idea is that we can rewrite these expressions here by assuming just a specific form for the initial state of the apparatus. So let me consider first this case in which the apparatus is in a pure state. Okay, that means that we know exactly how the apparatus is prepared. We don't have any classical uncertainty on our apparatus. We know exactly what is its states before interacting with the system, right? This is what one would like to know. Then in practice, it's not always possible, but in principle is what we want. So in that case, and I will also assume a particular observable of that I measure on the apparatus, just to be this generic observable R with eigenvalues Rk and eigenstates with these projectors Rk. So those are my K. This is over. So in that case, I can define this measurement operator. In this way, I call it MK, and I define it as this guy here. Okay, this operator is over the global system plus apparatus space, but these are states of the apparatus only. So this guy acts on the system only. Okay. So using this measurement operator, we can rewrite all these things in a very compact way. So for example, the probabilities of the outcomes now can be written in this way. And the state of the system after the measurement can be just written in this way. This is for the conditional state. And for unconditional one, I will just get this. So as you can see here, this is very similar to the expressions we got before for the projectors. Just instead of having projectors, we have these MKs. Now we have MK and MK dagger because they are not Hermitian in general. They can be Hermitian for some measurements, but they are not Hermitian in general. So in this case, it's a little bit more general. So the operators so the probabilities. So the operators that lead to the probabilities, so these ones here, are called effects in measurement theory. Okay, and are always positive, so that they fulfill this property. So we have this MK dagger, MK. They are always less or equal than the identity and positive definite. Those are co-POVs, which stands for positive operator valued measurement. And they completely determine the statistics of the measurement. So if I only talk about probability of obtaining my outcomes, I just need to know these operators here. And indeed, what they also fulfill is also this property. Which is equivalent to saying that the sum of all the probabilities get to 1. Okay, the probability of every measurement, the sum of the probabilities of every measurement is up to 1. Okay, so this is a general formalism for quantum measurements. We can even extend this a little bit more by introducing also some initial uncertainty on the state of the apparatus. So it is not very different if I do that. I just get the following thing. So in that case, I can have a statistical mixture. And now the previous expressions will translate to operators with 2 indices. So 2 subscripts, one that stands for the outcome of the measurement and the other that stands for one of the possible initial states of my apparatus. So in that case, these operators just get some extra factor that stands for the probability of the apparatus to be in a specific initial state. And of course, now we have very similar expressions for the probability of an outcome K. We just now need to sum over N, right? We need to sum over the different possible initial states of the apparatus. And same happens for the states of the system. So that's again the conditional. And for the unconditional, now we have the sum of over the case and the N. So over the outcomes and the possible initial states of the apparatus. Okay, so now, so there is a theorem which tell us that every set of operators Mk or Mkn, if we consider this case of uncertainty in the apparatus, that satisfy this condition, so the condition we have there, they describe a possible quantum measurement. Okay, so if we have an operator that satisfies this can be interpreted as a particular measurement of the system. And yeah. Okay, so having introduced this, let me see what's the time. Okay. So there are a lot of classes of quantum measurements, and depending on how we assume the properties of these operators, we will get different kind of measurements. So this, I will not enter into the details, but there are like efficient measurements, meaning the measurements that always reduce the entropy when I know the final state. So when I always know the outcome. There are complete measurements, there are bare measurements, there are a lot of classes of measurements. There's like a soup of measurements. And but I will not enter into the details. So I just wanted to tell you what is the general form, the general formalism. So of course, projective measurements are a particular case of these ones. No? So they are the case in which these measurement operators are just the projectors. Okay, so is there any question about this?
When you have when you have uncertainty in the initial state of the apparatus, it's not unique either, right?
It's not unique, yeah. It's not unique because I could select another observable here, for example, right? So I could add here some, let's say, unitary operation on the apparatus only, and this will not change the state of my system. Okay.
Thanks.
So yeah. So this somehow this recalls that there are many different measurements can lead to the same effective evolution for my system. Okay, so now I will introduce. So is there any other question about the measurements? Okay, otherwise I will introduce now what are called the quantum maps. So because the idea is that now we can use this like general approach of generalized measurements to describe open quantum systems. In a sense, it's like we can now assume that instead of having an apparatus here, we have a wall environment, right? Like a thermal reservoir or something or whatever environment. The point is that we can think about this environment as if it was measuring the system. Okay. So most of this formalism will apply to generate a formalism to describe open quantum systems evolution. So ni idea. Okay, so let's go for quantum maps. Okay, so in order to introduce the quantum maps, I would like to compare to the case of classical systems. No? In classical systems, we want to describe noisy processes, and in order to do that, what we allow is to introduce some stochasticity in the system, no? in the process that the system follows. So in general, we may have some input and state P would have some, let's say, different probabilities for being in different, let's say, discrete states. And this will change according like to some matrix M that contains that the conditional probabilities that I get some outcome given my income. So if I have n possible states, this will be n by n matrix. And this may describe a noisy process, right? So what are the requirements for this to be a legal evolution? So in general, the elements, so what we need to impose is that this state P prime should have like well-defined probabilities, right? So in order to do that, we need like the elements of this matrix M are non-negative. And we also need that they, when we sum over the first index, we will get 1. So the columns needs sum up to 1. So indeed, this can be just interpreted as these conditional probabilities, right? So in the case of quantum maps, we can apply a similar reasoning, right? So we have some output state rho prime, input state rho, and some super operator that transforms my initial state in my final state. So the state is the input. And this is called a super operator. This is just because it transforms one operator into another. Okay, so of course, the simplest example of a quantum map is just the unitary evolution, right? The unitary evolution is just to multiply the input by U on the left and U dagger on the right. This is the most simple case. However, of course, we want to go beyond this case, so which describes only closed systems, right? So one way to define quantum maps is just as before, right? We can just write this as a partial trace of a global evolution of my system and the environment and so on, and then trace out, and I get this state for my system. This is what we done before. But another approach is just to see what are the conditions that we need to impose on this object in order to be a legal evolution again. And the things that we need to impose are that this should preserve the trace, which is equivalent to preserving like these to be probabilities, right? So essentially the trace of E over rho needs to be 1, was in the initial state. The map should be convex linear, which means that if I apply the map to a mixture of states, I get the mixture of the maps applied to every possible initial state. And the other important property is that this map should be what is called completely positive. So complete positivity is a property which is stronger than positivity, as you can imagine. So positivity means that the final state should be a positive operator if the initial state is a positive operator, right? But complete positivity means that if we enlarge our system with other, let's say, auxiliary system, and we apply the map over my system times the identity over the other system, then this should be positive also. And of course, complete positivity implies positivity, but not the other way around. And one example is, for example, the transposition operation. If you transpose the density matrix, this is positive, but it's not completely positive. Okay, so it's not a legal evolution. It's not a physical evolution. If our map verifies these three properties, preserve the trace, is convex linear, and is complete positive, we say that it's a CPTP map. So this stands for completely positive and trace preserving. And these maps are also called quantum channels, okay? They are like the most general universal evolution for a quantum system, okay? So we can also define quantum operations. Quantum operations are CP, so they are completely positive, but they don't need to preserve the trace. So we just require that they have trace less or equal than 1. Okay, and in that case, they can be used, and at the end you renormalize the state. So the operations are, for example, what we have seen here before for having just one outcome of the system. Okay, in that case, so this guy here will be a quantum operation, and this guy here will be a quantum map. Okay. Well, of course, yeah. Yeah, okay. So then let me just set some properties of the CPTP maps. And wait, yeah, have time. So you see, just requiring these minimal assumptions, we can somehow define what is the most general physical evolution for a quantum system, or open quantum system. And then just because of that assumptions, we will get some properties that will be fulfilled in any case. So the first property is that the CPTP maps are always contractive. This means in the space of the density operators. And this means that they can only reduce the relative entropy between two different states. Do you know what is the relative entropy? It's like the Kullbaum-Leibler divergence for classical systems. It's a measure of the distinguishability between two states, okay, that tell us how different is rho for sigma. It is 0 if and only if these two are equal, and it is always greater or equal than 0. It is a quantity which is non-symmetric. So if I exchange this, I don't get the same number. But is so this is why it's not exactly a measure, but it's a distinguishability. So it's called a divergence. The classical analog of this is called the Kullback-Leibler divergence. So what this property means is that if I have two states, rho and sigma, they have some distinguishability, some relative entropy between them, and I apply the same map to both of them, I can only lose this distinguishability. So after the map, it's more difficult for me to distinguish between these two states than from the beginning. So I am losing information. Of course, in the case of the unitary evolution, I get the equality here. So another property is that any CPTP map has at least one invariant state or fixed point. It can have more than one, but at least there is one state that verifies this. And if the map is strictly contractive, so this is just contractive, strictly contractive will be only with the inequality, then this is unique. In that case, we may call it like the stationary state or steady state. Okay, another property is that, well, this is not exactly a property, but it's just, it's more a definition. Which is that the CPTP maps that verify that the identity operator is a fixed point, so are called unital maps. Or B-stochastic maps as well. So the analogous in the classical case are the maps that the rows also sum up to one, right? And they verify that the entropy of the map always increases. Okay. The map is unital, then the entropy of the state after applying the map is always greater than the one before. So we always lose information. And this, of course, includes a variety of evolutions, like, for example, mixture of unitaries, like pure decoherent processes, and much more. Another property, so that was the third one, fourth, is that is the set of CPTP maps possess a semigroup structure. Under concatenation. So this means that if I have two CPTP maps, E1 and E2, then the concatenation of these two is also a CPTP map. However, these two guys does not commute. So if I apply first E1 and then E2, it's not the same if I apply first E2 and then E1. But in both cases, the result is a CPTP map as well. And 5, so a CPTP map is invertible such that exists some e to the -1 such that e to the -1 concatenated with the original map is the identity if and only if this map is the okay. And then, so finally, I can write down what is called the Krauss theorem or representation theorem for the CPTP maps. Which sets essentially that if I have a map E that is CPTP, this is equivalent to say that this map has this form. Okay, with the operators verifying the property we have seen before for the measurements. Okay, so essentially what this theorem tells us is that we can interpret any CPTP map, so every general evolution on a quantum system, just as a set of random operations. So we have some initial state row, we will have some operations. Such that my initial state with some probability will go to. So I will apply with some probability each of those operations. With different probabilities. So this essentially means it's like the other way around that we have seen before. So before we have seen that, so we introduce explicitly the measurement, then say, okay, we have these measurement operators and this, if I forget about the outcomes, then I get something that is like a map. Right? Now we do the opposite. No, we start from the general requirement. What is the most general map? And then we get out that indeed we recover this structure that we have for the measurement. So what this means is that every map can be interpreted as a quantum measurement somehow. Of course, the composition on a map on Krauss operators is not unique. And this is again a consequence that there might be like, so the same process over my system, I can decompose different. So there are different global evolutions leading to the same effective dynamics of my system, right? But from the point of view of the system, I can always introduce one of these representations. Indeed, well, let's see. Okay. So let me just go very quickly to the last point I have for this session here. which is just the Markovian evolution. So until now, we have seen what is like the quantum maps formalisms. That is a very general class of evolutions. But however, very often we are interested in a subset of the of evolutions, which are like simple in some sense, and those are called Markovian evolutions. And the reason of why we want to reduce our interest to these Markovian evolutions is that they allow us to provide a continuous description of the system as well. No? Here in with the maps, we have like a instantaneous thing somehow. No, we have just initial state, final state. But in general, we would like also to have like differential equations to see what is the evolution over time of some process. In order to do that, so we can discuss, so how is the evolution of a system, right? So imagine I have some, well, let me now erase all this. Imagine I have some initial state rho 0 at t0, and then I go to a state that I call rho 2 at t2, right? But I want to split this, so this goes through a map, CPTP map. But now I want to split this in like in different time steps because I want to develop a continuous evolution, right? So now I look at what happens at time t1, right? So then I would like to split my map epsilon into combination of epsilon1 and epsilon2. But of course, what happens is that this is not in general possible. And why is that? No? So if, as I told you before, so the state at time t2 will be just the application of e to the initial state. And I can do the same also for the state at time 1, right? Rho 1 will be e1 over rho 0. But what happens when I want to try to now do the same for this piece? So the problem is that now, so since this just means that this is the trace over the environment of the, let's say, unitary over rho 0. This is this guy, and I can split the unitary. There is no problem of that as an application of first U1 and then U2, right? But sorry, this will be times the environment. Okay, this is over the system and the environment. But of course, rho 2. If I want to so this rho 2 essentially then is the unitary over the state of system and environment at time t1. But this, in general, is not what I will need to define a CPTP map, right? This is not, because this state is in general correlated. And I need that my initial state is uncorrelated. So that will be like the definition that I would like to this guy, but it's not possible in general. So in this sense, we talk about Markovianity as the maps that verify this property here. So they have an equality here. So Markovianity is like time divisibility. So in general, what we want is when this is possible, what we would like to do is to split the evolution in many small time steps and then obtain a differential equation that will have this kind of form. So this will get an operator, well-defined operator. Okay, this is what we want. This is so we want that this converts to some operator. And the most general form that, so this is also a theorem. The most general form that Markovian evolution has is the following. So this is called sometimes the lambda. So so essentially, what this theorem says is that if this operator has this form, then it is Markovian, and the other way around, right? So this is like the general form of this evolution. You can identify like a first term here, which is like the same as in the Schrodinger or von Neumann equation, right? But then we have an extra term, which is the dissipative part of the dynamics, which is ruled by this set of operators LK. And those are called Lindblad operators. They describe irreversible processes on the system. So, for example, it's very common to, so if we have, for example, let's say an harmonic oscillator that is interacting with a thermal environment, we will have, like here, the Hamiltonian of the harmonic oscillator, right? So like H will. Well, in general, I will use H bar equal to 1, okay? Because so at the beginning I was writing it and now I'm not writing it anymore. And these Lindblad operators in that case we will have like one for, let's say, like emission processes, minus, which will be like some rate times the ladder operator going down in the ladder, and some operator for absorption processes, just proportional to the to adding one quantum to one photon to the field, right? So in general, in that case, so these operators essentially what do is to make jump one. So we will add one photon when the system absorbs a photon from the environment, and go down by one photon when this photon is emitted on the environment. Okay. So this is just one example. There are many Lindblad equations, and of course, in many cases, we want to derive the Lindblad equation precisely from the model we have. Sometimes we start from a Hamiltonian of the system, Hamiltonian of the environment, and some interaction, and assuming just some weak coupling with the environment and another approximations, we get this equation. But for being a physical evolution, we need to have this form. Okay, let me just recall some properties of this Lindblad equation. And I finish with that. So, so the evolution has always one invariant state. So that we call this L of rho. So L of rho. And if this invariant state is unique, so we have that the evolution will go to that on infinite time. So if the invariant state is unique, then it is guaranteed that we will converge on the large time to that state. And a second property is that if we have a set of Lindblad operators that is self-adjoint, and this means that we have so all this the self-adjoint, so the joint of every operator is also inside the set. Then so then we can say that these operators come in pairs. So LK always have some other LK, right? Such that which is proportional to LK dagger. And so in that case, so this is what. So this is well, we will see this in the next sessions, but this is important to ensure detailed balance on this equation. So to ensure that we can reach, let's say, thermal state in the case of a thermal environment and so on. So, okay, so I think I finished with that. So is there any question about this part or the previous ones? I know everyone is tired right now, but
I have a couple, but I'll do just two. So you had the cross theorem on the right before, and you say that that you can always find a cross representation for the CPTP maps, right?
yes.
This theorem ensures that that representation exists, but doesn't give you a way to find them, right?
Yes, it's not unique.
How do you build up that representation?
So one way is, well, you can just try and verify that that this is fulfilled, right? Or what the people used to do is it depends on, so if you have a specific situation, in general, you don't know what will be the master equation. Okay? What you have to do is to derive it for the particular case you have, right? So this is just a very general thing of the theory, right?
Mm-hmm.
So you have to be sure that the equation you derive has this form. So you are assured that you have a well-defined evolution.
Yeah, the other question I have is related to that. That statement that this is the most general quantum Markovian evolution confused me a little bit, because if I remember correctly, when one did use this the Lindblad equation in general, you have to rely also on the rotating wave approximation.
Mm-hmm.
So any Markovian evolution
you can obtain
needs
also
rotating wave approximation as well?
No, you can obtain Lindblad form without the rotating wave approximation. You can with other approximations. But it's not, so there are many approximations in that sense. So there is also the rotating wave approximation can be applied to the global Hamiltonian or to, so you can do different things.
Okay, thanks.
But of course, that depends on the specific situation and so on. So in general, you need to, so in order to derive the right equation for your system, you need to assume just Hamiltonian of the system plus Hamiltonian of the environment plus interaction, and then derive, so we use all the derivation of the global evolution, and then start to introduce approximations. So usually the Born Markov approximation, and then either the rotating wave or some alternative approximation, so that you get some closed form in that sense. But yes, that is, I mean, it's important, but it's too much, I think, for for the scope of these mini curves.
Could you please explain what's the relation between time divisibility and the separation of time scales between the environment and the system?
Usually, you have time divisibility when you have some separation of time scales in the environment, so in the evolution of the environment. So if the environment, so essentially what you need is that somehow this state goes to this one, right? So you need that in general. The way to do that is to say that the environment like somehow relax rapidly, so that let's say the correlations between system and environment decay rapidly, or that they don't affect the system, the system of the evolution of the system afterwards. So they may be there, but perhaps in another part of the environment, not the part that is going to interact with the system next, right? So so for example, a nice way for me to think about this kind of evolution is like collisional models. In collisional models, what you have is like a system, and then your environment consists like in small units. So that the evolution of the system is just taking units and interact one at a time with the system. So that this interacts with that, but the probability that these units turn back and interact with the system again is negligible. So that in that case, you can really guarantee the Markovianity, right? So I like to think in open quantum systems a little bit in this way, right? Like if the environment is so big, so that your system interacts with different parts of the environment every time, but it's very improbable that it will interact with the same part again. So this is a way to intuitively understand this. Of course, using these kind of models, you can very quickly get the master equations as well.
So thank you very much. As far as I see, so what will happen is that the thermal bath will be measuring the system all the time.
Yeah.
Yeah. And we will assume that the thermal bath is large enough and composed of very small particles in such a way that it will be Markovian, and Markovian will be a non-correlated noise.
Exactly.
Yeah.
It will be like, so in this picture, indeed, if I start to put here after interaction, so I will get some correlation between system and environment in general. Yeah. And this is what guarantees, for example, that my system will thermalize. Otherwise, it would be impossible. But the evolution of the system only depends on this fresh part, right, of the environment. People interact with like fresh units. Not...
Okay, and that is the key to that makes possible to extend fluctuation theorems to quantum systems.
Well, you can also do in more general situations as well, but there's one way you can use.
Oh, okay.
Yeah.
And then you don't need to represent the thermal bath as a specific system, no? As is usually done in quantum mechanics, that you have to choose if you use a set of random harmonic oscillators so you can do it in general.
Well, yeah, I mean, also in this kind of models, you need to model of these units as well somehow. But yeah, it's not. But you don't need to assume very much details. I think perhaps less than in the other way. So yeah, I like a lot this kind of picture to model the open quantum systems. And regarding the fact that the environment measures the system, so this is right. We can interpret the environment as measuring the system, but we don't know a priori what is the basis that the environment is. What is the operator that the environment is using? No, this is because the Krauss decomposition is not unique. So in general, there may be like very many different compatible ways that the environment will be measuring the system.
Okay.
So it's not unique. So it's
And besides the fact that it's not unique, all these different representations will give the same results?
will be the same result for the system evolution.
Okay.
Only for the system evolution. And this is important for the thermodynamics because, for example, the change in entropy of the system or the change in the energy of the system, okay, it's the same. But depending on what are the operators that you use for the environment, for example, the heat exchange with the environment will be different because this describes a different process on the environment.
Okay. So work will be the same, but heat not. Heat
Work
doesn't.
work will be the same, yeah, because only depends on so if you only change the system Hamiltonian, then the work will be the same. But depending on how is the exchange with the environment, work can change because depending on how you interact with the environment, part of this energy. So I mean, so depending on how you change it with the environment, you will change the work. The change in the energy of the system is the one which will be the same. No, that doesn't matter.
I see. So the average energy will change the same, but because heat also changes, work will change.
Exactly, because part of the input energy, like for an external driving, can go into the environment.
Yeah.
So
yeah. Any other question? Yep.
So Jose Daniel say that that you can get from here that the noise is uncorrelated. I know that you can unravel this equation and you can see there in the stochastic master equation that that's actually the case, but I don't see here how do you get to that conclusion.
please say again.
How do you get to the conclusion that the noise is uncorrelated from the Lindblad equation? I know how to do it from the stochastic master equation that I guess you will show eventually, but
How do you see that this implies
that the noise is uncorrelated?
Yeah, I think it's difficult to see here. I mean, it's a theorem. I mean, it's a large derivation.
Okay.
But in principle, it's guaranteed if with this form.
Yeah.
Well, yeah. Yeah, the rates that appears inside the limit operators can be time dependent, but they need to be positive. Otherwise, you can have no Markovianity.
Thank you.
Some other questions? So if not, please thank the speaker again. So we will see tomorrow here at the same place, 8:30. Is there other announcements?
Tomorrow we start at 8:30 here.
me salió una pregunta. Si yo empiezo en el hamiltoniano del sistema,